So I said this is industrial strength software, and that's the focus. But that's not what I'm going to talk about. In part because it's been a while since I've been in industry, and it's been a while since I've written that kind of software and faced the kind of problems that you all face. And so instead, I thought I would tell you just some ideas and things that I think about as I think about how I want to compute in the future. And they really are ideas. They're not what I'd call even plans, because I need to do more research to understand better what can be possible. But I'm going to start with a sentence, and I want to see if you can predict the next phrase in this sentence. The program worked. You don't need to say it out loud. Just think in your head. Now it doesn't. Right? Has this happened to you? Yeah? Okay, so I teach a sophomore level, second year level undergraduate course in programming here at Mines. It's one of my favorite courses. We just finished this semester. Later on I'll show you a class project we did. And I love to ask this question about halfway through the semester. And easily over half of them say, oh yeah, because this is really troubling. And I can remember in 1973, I thought this had happened to me. And this is when I had just begun programming. Before I actually took a class, as a sophomore in college, I took my first course in computer programming. And then I realized, no, that computers really are predictable. You put in the same data that you put in yesterday, you're going to get the same output as you got yesterday. Right? And we rely on this heavily as we're trying to find errors in our programs. Okay. And then 20 years later, do you know what caused me to realize it was true? This is about the time I think I had my first dual processor machine. And it's also the first time, it was actually when Java became available. The very first demo for Java, when you downloaded Java 1.0, you got, there's a white paper, and it was all about concurrency. And it was about threads. And I didn't really understand, even the concept. And it's just me, being behind the times. Other people did. But okay, so now all of a sudden my programs might work, and then they wouldn't. Now, it turns out that my story here is related to a story that Les Hatton told at an SEG meeting in 1984. And the subject of his presentation was software quality. And he put up one equation. And he said that when he was younger, in 1969, he did not understand this. This was nonsense. Because he knew math, right? And he knew this was algebraically impossible. But then he began programming. And he was programming in Fortran. Now he understands, right? And then in 1983 or so, before he gave this presentation, he says he doesn't understand. And then he went on to explain why. See, it went deeper. He was trying to prove that software was correct, like other people were trying to do at the time. If you could run programs that would prove that your program is correct, wouldn't that be great, right? We would eliminate debugging and so on. He wasn't the only one trying to do this, but in our community in geophysics, he absolutely was. In fact, this particular project may have actually been the thing that took him out of geophysics. And actually, I shouldn't say that. He still is in geophysics, but he's in so many other things. I encourage you to go Google for Les Hatton and just find out what he's doing. He's amazing what he's doing. And so here he was, 10 years before me, and I'm sitting there. Did anybody go to this talk where he did this? You were there, Chuck, yeah. It was fascinating, right? And of course, when I'm sitting in the audience, and I said, well, I understand what that is. That's x equals x plus. What's the big deal? And he did actually go on and say that maybe he would have understood if it was written this way. This is ALGOL. This was the language that I studied as a sophomore in college, so it didn't bother me. Right? This is a statement in a computer language. It's not really an equation. And of course, today we might use something like this. But what Les was talking about went deeper than that. And I don't think that he was thinking about everything that I'm going to be talking about tonight, but But it turns out it's very much related to the first problem I said. My program worked, no it doesn't, I changed nothing. All right, so part of the reason that this equation was troubling Les and other people is that really it's a statement that represents at least 3 instructions that have to be executed as a sequence in time. And so the order here is just from the top down, right? So we load a value from memory into a register. Now that it's in the register, we can execute some instruction here. I'm just saying let's add 1 to it. So we're incrementing this register R, and then we have to put the value back in to memory. And all that works just fine. If we have 1 processor, I'll call this one the black processor. But when we have 2 processors, we can do the same thing, right, on each of them. Now, by the way, this is a very old picture. I want you to pretend like each of these processors has only 1 core. And on the computer I was using in 1994, I guess this is pretty much what I had. So I had 2 cores. And today, you realize that each one of these are Xeons. Each one of these Xeon processors now could have 18 cores. And I just learned, actually, recently, that the boards that are being made for these can now hold 8 of these Xeon processors. So that's now 144 cores that can all share memory. Right? And I'm going to assume that these 2 cores can share memory. Okay, but in this case, so the black represents the black core and the red represents the red core, and so this might happen, right? So black core loads 42. While he's incrementing his register, right? Each core has its own registers. The red core is loading a different number. Right? Eventually, the black core will store its result back into memory, and you get the idea, right? So this is fine. This is great, actually. We're not doing things in parallel. And maybe they're exactly synchronized, or maybe they're not, but this is all great. This is what we hope for. You heard of this data parallelism. This is what we mean. The problem comes when you actually try to take advantage of the fact that these cores really can share memory. Right? And this can be quite useful to take advantage of this fact. That's why the feature exists. That's why it probably makes sense not to just simply, on each core, pretend like it's a different node and just use NPI, as the mechanism for parallelism. Although that's possible, we're not really taking advantage of the hardware if we do that. Remember, 144 cores can all share memory. All right, so imagine now that the black core loads this number 42, and then in the very next cycle, the red core does the same thing. And I realize many of you know what's going to happen now, but the black core will store 43, and the red core will also store 43. That's probably not the answer you wanted if you were really trying to exploit the shared memory, right? What you might have hoped was something more like this. Because now the answer is going to be different. In other words, x now is not 43 anymore, it's 44. Okay, did you get that, right? So my program worked. This is the answer you probably wanted. But now it doesn't. And I didn't change anything. Okay. Because I'm not really capable, right, in the languages that we really want to use in geophysics, to coordinate the timing of these instructions. This is happening by the operating system. The hardware is actually helping to schedule these cores, the threads that are running on these cores and these processors. So this is a little bit like, imagine trying to prove a program is correct when you have this kind of a problem. This is the problem that Les was talking about. Okay, well, the good news is that we do have lots of opportunities for what we call data parallelism, or I'll just call it parallel array processing, because we have more than one X to process. And so often we have an array like this. Now this loop here is written in something like C or C++, but it could be a do loop in Fortran. And so we would start at I equals 0, right? And then do I equals 1, then I equals 2, and so on till we're all done. But because each of these x's can be really incremented independently, we can do this in parallel. And so this is the OpenMP way of doing this. And I'm leaving off a lot of flags that you might specify. Those flags might determine exactly which indices I get put onto this core and which go on a different core. Here's one way, right? So you could do half the array on the black core and half on the red. It might be like this, right? Or my favorite is if you put the word dynamic there after the parallel, you might get something like this. And what I like about this is that it might be that the red core got distracted. It might got busy. Or maybe it's not simply x equals x plus 1, or maybe it's something more complicated happening on each core, and it just takes longer for some indices than for others. And so this is a kind of a dynamic assignment of cores to elements of x in this array. All right, I'm going to simplify this now, because let's just call this parallel array processing. See, OpenMP is kind of funny, because it's a fantastic tool, because it's allowed us to exploit multi-core architectures for many years now, without making big changes to our software. In fact, you can turn off all the parallelism if you think you have a bug in your OpenMP pragma there, and just see if your program produces the same answer. That's really nice. But it's kind of funny, because the language says start at index 0, then do 1, and then do 2. Right? And so what you do with OpenMP is you say, no, that's a lie. I really mean just do all the I. Right? And so that's what I'm going to write it this way. Right? So we have multiple ways. And in fact, there are even languages now where loops kind of look like this. Python almost looks a little bit like this, right? For all I in some range. Okay, we won't worry about exactly what that range is. In fact, I'm going to assume that we're not also just simply adding 1 to x, right? We have other things that are more important to do. We might have loops inside loops. So this is just a two-dimensional array, and maybe that's one way to assign the threads or the cores to different indices. It might be this way. Often, depending upon what compute is, and maybe it's a finite difference stencil of some sort, but often, that will determine how you're going to want to partition the work among these different cores. Okay. All right, so I'm going to, again, further simplify things and imagine that we could have loops inside loops. This could be a three-dimensional array, but I could keep going, right? So maybe these are 3 space dimensions. We might add another dimension, another outer loop over time if we're stepping over time in a finite difference simulation of waves, something like that. But easy stuff, parallel array processing. So I'm going to keep kind of simplifying. Right? Just imagine we're going to loop over all these. By the way, I can type this faster than just about anybody except Jeff Emanuel. I mean, these kinds of loops just roll off my fingers. Sometimes my students are impressed by how quickly I can write code. And they're often watching me type loops like this. I'm sure that many of you type these kinds of loops in your programs. Right? They should not be impressed by this. Right? And you wouldn't be either. And I'll tell you even more why in a moment. Okay, so let's just say we're looping over all the indices, but let's make it even simpler. Looping over all samples. And in a lot of things we do today, we're doing this, loop over all samples, compute, inside some iterative solver. Right? So we'll keep doing this until the solver converges, right? Whatever that means. Right? So that's what I mean by while not done. So while not done, loop over all samples and do a computation. You've seen many examples of this kind of thing at this meeting. And I'm going to point to one of them by Jinming, where he showed you his unfaulting shifts earlier today. Excuse me. All right, so what I want to show you is what's actually happening inside the iterative solver that he is using. And so he starts with shifts are initially 0. And then he's estimated the slips at the faults already. And so what you'll see is that when I run the movie, you'll see at the faults, right away you'll see a discontinuity in shift. And then he's going to distribute that strain at the fault away from the faults using a conjugate gradient method. Right? So that's actually what's going on. Sorry, let's see if I can get this right. There we go. I'm too chicken to do a live demo, so I made movies. All right, so did you see that, right? So the solution is gradually moving away from the faults, into the fault blocks, distributing the strain. Right? And this is the final answer that we get, I guess, after He's done, right? He has a loop, like many of us would, while not done. He has to loop over actually multiple three-dimensional arrays with code like that you saw before. And we do this in a thread-hot way. If you watch the CPU meters, when he is running this software, they are pegged out. They're just like what Chuck Moser was showing. We are running at 100% on, if you run it on a 16-core machine, all 16 cores are really going. Okay, now I want you to imagine a scenario, and this is one I posed to Jinming. I say, take these shifts now, and I want to know as an interpreter, what's going to happen if I say, I'm not sure that that fault should be there. Right? So I want to take out one fault, which means there really aren't any slips there anymore. Recompute the solution now. Okay, now remember what he's doing. While not done, he's looping over all samples in this tiny image. If this was a big image, you would hardly see any change at all. Right? Because I'm zoomed in on part of it, what you will see is a change really only near the fault. The image is not changing anywhere else. All those cores running at 100%. Right? I'm still feeling good, right? But wait a minute, I feel like I've wasted some of the computation because part of the image was done after the first, maybe the second iteration. But the part near the fault is the part that wasn't done. All right, so now put the fault back. I mean, this is easy to imagine happening. Maybe, the interpreter sits down and we've pre-computed all the surfaces and all the slips and everything, and then the interpreter just says, I think there's a fault here. Boom, yeah, we agree. So we put that in there and we show you the shifts and we're able to unfault the image, and you can sort of experiment with, reversing geologic time by saying, I think this fault came before that one. This is not just a thought experiment. It's something we really might want to try to do, which is like put back the fault that we took out. I think I have a movie of that. Again, the solution is changing only near the fault. A fault is a two-dimensional surface, so the computational burden here is like a dimension smaller than our loops, right, over 3 dimensions. Right? In other words, the computation cost is proportional to the area of the fault and some distance away from the fault, but really it's the area of the fault that determines the cost, not the size of this image. Right? All thread hot. It looks great when I look at my CPU meters, but I'm less impressed by that today. Right? So there are 2 things that I don't like about this loop here that trouble me, and one of them is the word while, and the other is all. The word while I don't like is because I don't really even know, for the example I showed you, what a good measure of convergence should be. I mean, we show examples of the objective function going down, right? And that's a single number. But think about it, right? In the example I just showed, what is that single number telling you? It's telling you what the change in the entire image. Most of the image didn't change. Right? It was just the part near the fault. Now, I don't want you to think that this is not, the while here has nothing to do with wave propagation time. Right? This is computer while. Right? It could be a computer for loop, but we'll say while, not done. Okay, so the other thing which I've already talked about, that I don't like, is this word all, because this means that we are looping over all the samples in our array or our model or whatever, whether or not they're actually changing. Okay, so you know what I want to change them to now, and this is where the title of my presentation comes from. Right? I want to compute only where not done. In fact, I'm going to say that we are never done. Right? I mean, there's always new data coming. Right? When are we done? Right? And so imagine that, we now have a new well log. How would that change my full waveform inversion? So only for those samples, where we need work. Like where is the error in our solution? The residual, where is it largest? Right? And so why don't we do this? Right? Why don't we write loops like this? I think part of the reason is, how are you going to use OpenMP, right, for something like this? Right? Remember, you have these arrays with loops, for I equals 0 to n in any number of dimensions. Right? That works pretty well. But how do you even iterate over all the samples near the fault? Right? Or starting at the fault, push the computation away from the fault until you don't notice any change anymore. Right? That's what I mean by we're not done. But how do you do that? Right? How do you organize that kind of a parallel computation? It's not as simple as the parallel array processing I showed before. It's a little bit more like this. Now, this is going to be an extreme. This is the class exercise that we did just a few weeks ago here at Mines in my course. It's a simulation. CSCI 261 is just the course number. In the box, here, I'll label them. In that box you see are ants, and the red squares are food. Right, this is actually modeled after a toy that some of you may have had. I never had this toy. I mean, the box says break resistant. What does that mean? I mean, a lawyer wrote that. Yeah, and escape proof. Yeah, so I don't think my parents let me have one of these. But that's okay. We can simulate these, and they are escape proof if we do them inside a computer. If you never had one of those toys, just pretend like it's a corporation instead. Right? And the food is just revenue, and it's your job to go get some. Right? And so here you go. Right? You're going to go out and get some, okay, we'll call them ants. Now, as the ants move, let's see if I can stop this. Yeah, good, I can freeze it. Okay, so as the ants move, they leave a trail of pheromone. Some of you realize this is actually a numerical algorithm which is used in optimization. Right? In geophysics, in fact, it's similar to what's happening in ant tracking for detecting faults. But they leave a trail, and each one of the ants behaves rather independently. Right? Each ant, knows only a little 3x3 neighborhood, and it will choose, generally to try to follow a path that was laid down by another ant. Now, some of the ants are red. And those are the ones that have picked up food. And their job is to get the food home, right? So that's the task here. Whoops, sorry. Right, go find the food and bring it home. So when they find food, they turn around, they turn red, and then turn around and they go back. Right, now, it's a fun class exercise, and at the end of the semester, we race, right? And I go around giving high fives to all the students that beat me, right? And getting all the food home. And I'm not going to wait for all this to get home. But I want you to imagine how we wrote this program. Right? So first of all, how do we draw the world? There is a loop, right, over all samples. Right? Because we have to loop over samples to figure out all locations in the grid. How much pheromone is there? So we fill a rectangle with green. Is there food there? The food changes because ants are taking the food. So we loop over and we draw the world. Okay? Now, while we're drawing the world, nothing else is happening because this is happening in a single core. This is happening in a single thread. The ants aren't moving. Right? So, all right, now we have to make each ant behave. And so this is actually where the students got to fiddle around. You say, you can. I put in rules on what the ant could know. Like I didn't allow, a god ant or something like that to steer them. Or I didn't allow ant radar. But just, real simple computations and try to get the food back home. So what happens is, after we draw the farm, we then start drawing, or make each of the ants move. Okay, now that we've made every ant move, we draw the farm again. Right? And we just keep doing that in one core. All right, now, but this exercise was inspired by a movie which I showed my students that I found on YouTube. So we watched this movie. Actually, the YouTube video, it's actually 2.5 hours long. And it goes into way more detail than I will talk about here. But I put the name Rich Hickey and Ants Demo, and that's all you need to find this video. This is, in fact, his ant farm. If you go on YouTube, you'll eventually get to see him run this code. Right? So you can see where we got the idea for our class. But this code is very different. Each ant here is running in its own core, or its own thread, I should say. There are 49 of them. They are all working independently. They are autonomous. If there is an ant next door, I mean, they're still looking at this 3x3 little patch of the farm that they can see. If there's an ant next door, well, there might be some coordination, right? Because this program will guarantee that no two ants ever exist in the same location. Okay? The other program we wrote didn't do that. Right? But think about this. They are all running in their own threads. Moreover, in order to draw this, here, I'm going to stop. In order to draw this, I don't have to do what I just did with the movie. I don't have to stop the world. I mean, just imagine something simple. Count how many people are left here at, what, 5:45 in the evening, the last day of our meeting, right? It's much easier to count you because you're sitting still. If this was a break, it would be really hard to count everybody. I'd start counting over here, and then what would happen is people would move, right, while I'm counting. You've all seen this problem, right? So what's interesting about this application is that the code that's doing the rendering is running in a separate thread, concurrently, at the same time. And it's like we have a camera with infinite shutter speed. Right? It's able to accurately render the world, the farm in this case, without stopping it. And each ant is behaving independently. I don't know how to do this with OpenMP. Right? And you're thinking, well, that's okay because I don't really want to simulate ants. Okay, I don't either, but from now on, when I use the word ant, I want you to think of that as just another word for thread, or core, or processor. Right, so for the Ritchicke's demo, if we've got 49 ants and one rendering thread, that's 50 threads. If you had a processor with 50 cores, it would be exploiting all of them. Right? You would get almost this factor of 50 speed up. Okay, so I'm going to make this a little bit closer to home by imagining we have a set of scattered porosities, and so the colors represent different porosity values. It could be anything. In fact, I really want you to think about this as more abstract, but let's just pretend like that's something that you might get in well measurements or something like that. So our goal will be to interpolate measurements where we don't have them, say at this location. So we're going to put an ant there. And the simple interpolation I mean here is just called nearest neighbor interpolation. This ant is going to do some kind of a spiral walk. It's an ant that walks in a circle until it finds a data value. In this case, it's the value that's light blue. It takes that value, puts it at the location where the ant first started, and we've now interpolated one value. It's really easy to imagine how you can do this repeatedly over and over again for every sample that you don't have. And so this is what the program would look like if you just have one ant. So what are you going to do? You're just going to have a loop for all I1. When we get to the bottom, we're going to go to I2, right? And so it's just doing nearest neighbor interpolation. That very simple algorithm. Okay, but the point of this is that we want to do this faster. Right? That's why I'm talking about it. Right? And this is a good example of where OpenMP would be just fine. You could have 10 ants. Right? Everything runs faster now. Let's make 100 ants. There we go. Okay, so now you can see the interpolations go much quicker, and this is, of course, a toy. It's an animation that I made for this presentation, but hey, it's not hard to imagine, because what happened? When you're interpolating at one point, it has no impact on the interpolation at an adjacent point. Of course it's parallel, right? So we'd have no trouble with something like OpenMP. Now the interpolation is not very good. It kind of implies that halfway between everywhere you've got a measurement, you've got a fault, and of course that doesn't make sense. So we would try to use some other interpolation. And one I have talked about at meetings like this in the past is an algorithm called Simpson interpolation. It's also called natural neighbor interpolation. It's very similar. It's very easy to implement. You know, it's a lot easier to implement than something like Kriging. In a lot of cases, it can be much faster. Right? And it has other nice properties. But I'll just tell you real simply how the algorithm works. We start just like we did with the simple interpolation. Right? Put an ant there. Go ahead and do the spiral search until we find the nearest data value. And here comes the difference. Now, instead of just taking that value and copying it to the center of the circle where the ant is, we're going to take that value and accumulate it everywhere inside the circle. Right? This is a beautiful algorithm, described very nicely in a paper 10 years ago. Beautiful because it is so simple. If you go and learn about Simpson interpolation on the web, you will find almost certainly many more complicated implementations that talk about first building a Delaunay triangulation. And, it's really easy. So if you ever get stuck and you just need to interpolate some scattered data real quickly, you can implement this in easily, like a half hour. Okay, now you have to do one more thing, which is as you are accumulating the light blue value, you need to also keep a counter. Right? For every sample in that circle, right, we're going to add the blue value to X, and we're also going to add 1 to a count. Right? And the reason is that, well, you'll see why. Because I'm going to move the ant somewhere else. Just imagine later on we're down here, and now we accumulate a different value. Right? It'll be, again, the nearest value in this case is dark blue. And where the values overlap, we're going to want the average. How do you get the average? You have a numerator, which is the sum of values. You have a denominator, which is the number of values you have summed. And that's why we have to keep accumulating both the x values and the count n. But you see that they're very similar to the x equals x plus 1 problem that Les Hatton was talking about so many years ago. All right, and I think you may also be able to see why this is not going to be so easy to do with something like OpenMP. I actually give this as an assignment in a graduate course that I've taught at Mines, and no student has ever really come up with a good solution for this problem. And I think the answer, and this includes people like Simon Lowe and Stephen Compton, who are really good programmers and really would take it as a challenge to do it well. And so here's the problem. Where those circles overlap, if we are doing this in parallel with my black core and my red core, so imagine now you have two ants that are working in parallel. Where there's overlap, it is quite possible that both ants are going to be updating the same x and the same n at the same time, and we're going to have that race condition that I showed you at the beginning. Right? And so I always like to run this, pretend let's just ignore that problem. And it's really fun because we run it and you get one answer, you run it again, you get a different answer, you run it again, you get a different answer. Right. Now, this is just for interpolation, but think about this. What's happening here is our stencil, the area that's affected by where the ant is, depends on a computation that we have to perform. Right? There's no way ahead of time to partition the world into pieces that won't overlap, right? I mean, you might come up with a scheme that where you could avoid any possible conflict, right, or concurrency problems, but that's implementing that scheme would end up costing more than the interpolation itself. And I think there are many problems like this, but we don't even tend to think about them in geophysics because you can't use OpenMP, and if you try to do it, well, there's no good way to do it for things like this. Okay, so here's, in my mind for many years, long before I saw the ants demo or anything like that, I've had in my mind that algorithms, the way we program computers has to change. And it was the ants demo that made me think, oh, this might be the trick. Because the way Rich Hickey did it, the way he made it so he didn't have to stop the world or he didn't have to do each ant independently or one at a time in sequence. When I saw that, I realized this was something I was looking for. It was a way to program, without loops, without arrays, because that's what, I don't want to have to loop over all samples. I want to go only where not done. And so this is kind of what I had in mind. Unleashing an army of autonomous processors, or cores, right? And if you get more cores, just your army got bigger. And just go solve the problem, right? So here is Simpson interpolation, right? Without any predefined strategy or stencil. Just each core, each thread in this case, because I don't have that many cores in the laptop I did this with, but it's just working independently. And you can imagine, right, that the circles in which the scattering is being done, the accumulation is being done, they are overlapping like crazy. Because, remember the ant location is the center of a circle. Right? So the ants there's got to be conflicts, yet this is using just a modification of Rich Hickey's demo to make this happen. Now, you might think there must be a cost associated with this, and there certainly is. And so you might try to minimize the chance of two ants trying to update the same location by maybe doing something like this, right? There's no reason why you have to start on the left and work your way from left to right. These are like flying ants or parachuting ants or something. They're just going to raining ants. That's what we're raining ants onto the problem here. Right? So raindrops, where are they going to fall? Right? So I won't, actually try to show you by subtracting images or anything that the solution you get here, or with the previous movie, or if I run this again, is going to be exactly the same. And yet each ant is just working independently with a very simple algorithm, which I explained to you. Finds the nearest sample, accumulates in a circle centered at the ant's location. All right, I won't let the thing go on. But that's what I mean by we're not done compute. Right? I don't think we're ever done. There's going to be new data coming in all the time, and when that happens, we want to be just throw cores at it. Throw cores at that location. And it's not just spatial location. It might be there's a time dimension. Right? So for the times and for the spatial locations where we're not done, compute. So this is something that I want to look at. And I don't know if it's going to work. Every program I've shown you today is a toy. It's a toy for me to learn. And that's why Rich Hickey wrote his demo, because he was trying to teach other people about his approach to solving this problem. I don't know if it's going to work for the problems that we have. I really want to know. And at the same time, there is a place for while, but it's this one. Thank you.